Welcome. In this explainer, we're going to tackle a really fascinating chemical mystery. You've probably noticed it yourself. Why does a hot cup of coffee always get cold, but something like an instant cold pack can get cold all by itself? It feels like it shouldn't work that way, right? Well, today we're going to solve it, and in the process we'll uncover a fundamental rule about how our entire universe works.
So picture this. Meet Aarav. He's got his morning coffee and it's doing what coffee does. It's cooling down, releasing its heat into the room. But then he thinks about that instant cold pack in his first aid kit. You crack it and it gets icy cold, doing the exact opposite. It absorbs heat from its surroundings. How on earth can both of these things happen all on their own? It really seems like energy is breaking its own rules.
All right, to solve this puzzle, Aarav basically has to become a detective. He's on the hunt for the universe's two most important laws for energy and change. And his investigation starts with clue number 1, figuring out how to properly track where the energy is going.
So, our first clue is all about energy accounting. It's kind of like balancing a budget. You can't figure out where your money is going if you don't first define what's in your account and what's outside of it. Same thing with energy. In thermodynamics, we start by drawing a simple line in the sand. On one side, you've got the system. That's just the thing we're actually watching. In this case, Aarav's cup of coffee. And on the other side, we have the surroundings, which is, and I mean this literally, everything else in the universe.
Now that we've got our terms straight, we can introduce the first big rule. And the first law of thermodynamics is just beautiful in its simplicity. It says that the total amount of energy in the universe is constant. You can't create it, you can't destroy it, all you can do is move it around between the system and its surroundings.
And of course, scientists have a tidy little equation for this. It just says that any change in a system's internal energy, that's delta U, has to come from one of two places, either heat flowing in or out, that's Q, or work being done, that's W. Think of work like a piston moving in an engine.
And to keep track of this flow, there's a really easy sign convention. If energy goes into the system, we call it positive. If energy leaves the system, we call it negative. That's it. It's like a bank account for energy. Okay, so for most everyday things, like a coffee cup just sitting on a table, we can pretty much ignore the work part of that equation. It's not really relevant. This lets scientists use a much more convenient measure called enthalpy, or delta H. For our purposes, you can just think of it as the heat that's flowing in or out.
And this brings us right back to Aarav's mystery. If that delta H value is negative, the process is called exothermic. It releases heat, just like his cooling coffee. If delta H is positive, it's endothermic. It absorbs heat, making things feel cold, just like that instant cold pack.
But wait a minute, this helps us label things, but it doesn't actually solve the mystery, does it? It doesn't explain why these things happen spontaneously. If energy is just being moved around, why does heat always flow from the hot coffee to the cool room and never the other way around? The first law alone just can't tell us. We're missing a piece of the puzzle.
To find that missing piece, we need our second clue. And this one has nothing to do with the amount of energy, but everything to do with how that energy is spread out. It's all about a concept that you might call chaos or disorder.
Aarav's next clue is something called entropy, which we represent with delta S. Now, it sounds super complicated, but honestly, it's just a way to measure randomness or disorder. The more possible ways there are to arrange something, the higher its entropy.
Think about it like this. Imagine a brand new deck of cards, fresh out of the box, perfectly sorted by suit and number. This is a state of very, very low entropy. Why? Because there's basically only one way for the cards to be in that perfect order. It's incredibly unlikely to happen just by chance.
Now, what happens if you just throw that deck up in the air? The cards flutter down into a completely random, jumbled mess. That is a state of high entropy. There are millions upon millions of ways for those cards to be disordered, making it a way more probable outcome.
And that simple example perfectly illustrates the second law of thermodynamics. It says that for any spontaneous process, anything that just happens on its own, the total disorder, the total entropy of the universe must increase. The universe is constantly, unstoppably moving from order toward chaos.
Okay, so Aarav now has his two crucial clues: enthalpy, which is the heat change, and entropy, the change in disorder. The final step is to put them together into one single powerful tool that can predict whether a reaction will happen all by itself.
So, to get our final verdict on any reaction, we have to look at two competing drives. There's the drive to lose energy, that's our enthalpy, and then there's the drive to increase disorder, that's entropy. And the referee that decides which one wins this cosmic tug-of-war is our final ingredient, temperature.
And here it is, the Gibbs Free Energy equation. This is the ultimate decider. Delta G, the change in Gibbs Free Energy, pulls together the heat change, the disorder change, and the temperature into one master equation that tells us what's going to happen.
And the rule here is an absolute game changer. It's so simple. If delta G ends up being negative, the process is spontaneous. It's like a ball rolling downhill. It just happens. If delta G is positive, it's non-spontaneous. You'd have to push that ball uphill. And if it's zero, the system is perfectly balanced at equilibrium.
All right, this is the moment of truth. Aarav has all the tools he needs. Let's use this powerful Gibbs Free Energy equation and finally solve the mystery of the hot coffee and the instant cold pack.
This table is basically our ultimate cheat sheet for predicting the future. It shows exactly how enthalpy and entropy fight it out. For example, check out that bottom row. A reaction that absorbs heat but creates a lot of disorder can be spontaneous, but only if the temperature is high enough. It's this constant balancing act, and temperature is the key. And here it is, the big reveal. The hot coffee cools down because it's exothermic. It releases heat, and that escaping heat creates more random motion and disorder in the air molecules of the room. Both factors push towards spontaneity, making delta G negative. Easy. But the cold pack, that's endothermic. It absorbs heat, which works against it. So why does it happen? Well, the reaction inside involves a solid salt dissolving in water. The particles break free from their rigid perfect crystal structure and get to zip around randomly in the liquid. This creates a massive increase in disorder, a huge jump in entropy. That entropy term in the equation becomes so big and positive that it completely overpowers the unfavorable heat absorption, making the overall delta G negative. And that is why it happens spontaneously.
So what's the big takeaway here? It's that a reaction doesn't just happen because it releases heat. Spontaneity is a cosmic tug-of-war. It's a delicate balance between a system's drive to reach a lower energy state and the entire universe's relentless, unstoppable march toward greater and greater disorder.
This fundamental balance between energy and entropy doesn't just explain coffee and cold packs. It literally governs everything from the way stars form to the incredibly complex chemical reactions that are keeping you and me alive right now. Knowing these rules, what does it make you want